Okay, so today we're going to determine if the total force acting on an object is equal to 0 or not, and write a mathematical expression describing the forces and motion of an object. So if we do a free body diagram of this box, you have force of gravity, applied force, normal force, and friction. Okay, that is step 1 of 5. All right. Step 2 is to determine which direction is positive. I'm going to make the way it's moving, and typically I'm going to suggest that, make the way it's moving the positive direction. So I'm going to have to the right be a positive x direction, and I'm going to have up be the positive y direction. Okay, that's step 2. Step 3 is to look at the forces in the x direction and say, when they add them up, are they equal to 0? And we're going to ask the same question for the forces in the y direction. Do the sum of the forces equal 0? Okay. To answer this, we're going to look at the motion, meaning that, and we're going to ask ourselves, is inertia happy? Is inertia doing what it wants to do in that direction? Not the free body diagram. Okay. So we're asking ourselves, is inertia happy? Is inertia doing what it wants to do? Okay. So inertia, if it's at rest, inertia wants to stay at rest. If inertia is in motion, what does it want to do? Stay in motion, specifically at a constant velocity. Okay, so in the x direction, is the sum of the forces equal to 0? Think. Tell your neighbor and tell them why or why not. Correct answer is no. Why not? Because it's speeding up. I am not looking at the free body diagram to figure this out. I'm looking at the motion. Okay, it is speeding up, so therefore not equal to 0. Okay, tell your neighbor if the sum of the forces in the y direction are equal to 0. Tell them why or why not. Correct answer is?
Yes. Sorry, yes.
It is, because it's at rest in the y direction. Okay. Good with that? That was step 3. This is an important conceptual step. Okay. Step 4. We are adding up. I want to add up all the forces that are going on in the x direction. Okay. So what forces are acting just in the x direction? And are they positive or negative? I got friction. Is it positive or negative? Negative. So I have negative friction plus a positive applied force. Okay. So I could write it like that. I definitely wouldn't, but that's just trying to teach. I would tend to write it like this. Okay, I'm adding up the forces just in the x direction. Kind of has a projectile motion flavor to it, like your horizontal and your vertical chart. Okay, kind of see what we're doing there. Why don't you do the y direction? Some of the forces in the y direction. You have normal force minus force of gravity equals 0. Good with that? Okay. Oh. Sorry. There. Okay. That's step 4. Step 5 is to set it up what they're equal to. We'll start with the y direction because that's the easiest. We discerned already in step 3 that the sum of the forces are equal to 0. Well, these are the forces, and we're adding them up that are in the y direction. Therefore, they have to equal 0. You all right with that? Okay. In the x direction, we said they're not equal to 0. What is it equal to? I don't know, but it's not 0. So the nice thing about algebra, we don't have to know what the value is. We can just represent that with a variable. The net force, the total force, is equal to all the forces in the x direction added up. Okay? But we're not going to stop there. We know from Newton's second law that the net force is equal to mass times acceleration. You all right with that? So what I'm going to do is I'm going to take mass times acceleration, substitute it in for net force. And that's going to be equal to mass times acceleration in the x direction. So when you're setting this up, if it's not equal to 0, you're just going to write this straight away. Okay? Add up all the forces in that direction and set it up equal to mass times acceleration in that direction. Good with that? And that is your setup. If you can own this process, it will go very well for you. Okay, Sean.
What if the force is diagonal, like goes through x angle?
So funny you should ask. Any questions on this? Okay. Here's the 5 steps. Free body diagram. Figure out which directions are positive. Ask yourself, is the sum of the forces in the x direction and y direction, are those equal to 0? By looking at the motion, not the free body diagram. And then step 4 is to add up the forces just in the x and just in the y direction. And then step 5 is set them equal to something, either 0 or mass times acceleration, depending on the circumstance. Okay? The steps are in the PowerPoint right here, how you bake a force problem. Okay? So, go ahead and draw a free body diagram of this scenario. How'd we do? Any better? All right. So move on to step 2. I'm going to make to the left positive, up positive. So moving to the left. Step 3, determining if the sum of the forces are equal to 0 or not in the y direction. Why don't you go ahead and figure that out? Tell your neighbor what your decision is in the y direction. In the y direction, what do you think?
I don't know the question. Dude, I don't even know. I'm just saying it's not. Get it right.
In the y direction, is the sum of the forces equal to 0?
Yeah.
How do you know? Because it's not moving up or down. It's at rest in the y direction. Right? We are not looking at this free body diagram. We're looking at the motion. Okay? So, is equal to 0. What about the x direction? Is the sum of the forces equal to 0 in the x direction? Tell your neighbor why or why not.
You're not looking at the free body diagram. You're looking at the motion at its constant velocity.
Okay, correct answer is?
Yes.
It is equal to 0. Is inertia doing what it wants to do? Yes, it is. Okay, do not look at this to determine that question. All right, with that, does this make sense what I'm saying? Don't look at the free body diagram. Look at the story problem. Look at the situation. Look at the motion. Okay? This is a big pitfall. We're like, oh, it's moving. Is it possible for something to be moving and inertia to be happy? Yes. If it's maintaining a constant velocity, like yes. Okay. And this is a distractor. It's 2 meters a second. I don't care what that number is. If it's a constant velocity, you know the sum of the forces are equal to 0. Okay, regardless of how fast. All right. Step 4 is to add up the forces going on just in the x direction and just in the y direction. So, what forces are acting just in the x direction?
Tension, friction.
Okay, we got friction is tension acting solely 100% just in the x direction. But is part of it?
Yeah.
Oh man, what should we do? We have a force at an angle.
Trigonometry?
We should.
No.
Oh my.
No.
Folks, I told you, it doesn't go away. Things just keep. So, I'm not going to solve for it right now. I'm just going to represent that with an FTX. So, force of tension in the x direction. And the y direction, FTY. Okay, I've got something at an angle and then break it up into components. Okay, so now go ahead and finish. Beat me to the end. How do you do? And that's your setup. Okay, so this is what you're doing on your worksheet for day 2, which is due on Thursday. Say it again. We're just setting things up. Okay, got one more example problem. Tomorrow we'll go over the test. Okay, free body diagram of the car parked on a hill. Make your force of gravity long. That'll be helpful in this. How do you do? Okay. Don't draw this next thing. Do not draw this. There's my x-axis. There's my y-axis. How many force vectors are we going to need to break up into components? 2. 2 of them do not lie on the axis. Ugh. Check out this trick. Math people get a little disgruntled by this. But what I'm going to do, if I ever find myself on a hill, an incline, a ramp, a slide, anything where the surface is tilted like this, what I'm going to do, I'm going to grab the x-axis and I'm going to tilt it. So now I'm going to make the axis like this. I'm going to make the x-axis parallel to the ramp. and the y-axis perpendicular to the ramp. You do that every time, anytime you're on an incline. Okay, so now, how many vectors do we need to break up into components? Just gravity. Okay, here's a memorized thing. Very few things that tell you to memorize. This is it. This is one of them. Whatever this angle is, that's the same angle between the y-axis and the force of gravity. I could give you a geometric proof of that. Most of you don't care.
Let's see it. I want to see it. Jason English.
Do English first.
I'll do it after I get done. Make sure I get done. Okay? So, here's my FGY. And here's my FGX. And I'm going to make my axes, make my positive X, positive down the ramp, and my positive Y perpendicular. So at this point, I'm going to stop saying horizontal direction and vertical direction like I did in projectile motion, and just say in the X direction and the Y direction, because X and Y no longer are stuck to horizontal and vertical. Okay, so go ahead and set it up. Beat me to the end. How do we do? As it's parked.
What?
How do you know it's equal 0? Because it's at rest. Okay, good with that. So that's what you need to do for day 2. All those things you did a free body diagram of, you can do that. Okay. So here's your geometry proof. So I've got this line, like the ground, and this line, they're parallel. Okay. This line and this line are parallel. Okay. So this, oh, gross. That guy is congruent to this guy. I don't know what the name of that is. And this guy is congruent to this guy. Right here we have a right angle. So this is complementary to that right angle. Well, we also have a right angle here, and this thing is complementary to this red angle as well. So by whatever property, that's not SOHCAHTOA.
Your ITT.
Have a great rest of the day, folks.